Okay, so I've shown enough about cardinality that I need to in order to like continue with the computability stuff. But I feel like to stop there and to just kind of move on would be to kind of like rip people off in terms of giving them like a full understanding, not of cardinality. And what I mean by that is we really don't have like a full definition for it yet. And also what I mean by full story, I put like an asterisk here, is cardinality is a giant field of math. There's tons to say. So what I mean by full story is basically like to the average person that's interested in math, like what would I hope what's like the most essential things that I want them to know about cardinality. So that's kind of what I wanted to specify in a little quick video. Hopefully I can make this quick. Kind of finish ourselves up and develop and kind of write down a full definition and say a little bit about it and kind of state the continuum hypothesis, which is kind of the big kind of central pivoting thing about the theory. So to recap what we've done so far, the first definition that we kind of made was that we said that the cardinality of a set is the number of things in it. This is kind of the naive, basic starting point definition of cardinality. And it's perfectly fine. For finite sets, this is great. Then we made an attempt to extend the cardinality definition to infinite sets, or at least to kind of come up with an understanding of infinity that was kind of in line with this earlier definition. And so we refined, we talked about functions, and we kind of like looked closely at what functions really represented, especially injective functions, and we kind of from that defined the second definition, which is we said that the cardinality of a set really, and this is just an extension of this, is the smallest subset of the natural numbers which has a bijection with the set itself. So for example, if A is equal to A, B, C, the cardinality is 3, not simply because A, B, and C are elements of the set, although it is like that, but kind of to be a little more mature about it, it's because we can kind of assign A to the number 1, we can assign B to the number 2, and we can assign C to the number 3. And so this is a bijection between 1, 2, 3 and A, B, C, and obviously that's the only subset. It's the only subset of the natural numbers. Well, it's the smallest subset of the natural numbers that's ordered that has a bijection with it. So that's the cardinality second definition. And from that, we got kind of like a notion of countability as like a type of infinity. Works for finite sets. But as we saw, not all infinite sets. We were kind of cruising for a while and showing that almost anything we thought of was countable, and then we realized that not everything was countable. So there are infinities bigger than n. And this is not just kind of a like a mathy, just ridiculous kind of no practical application. This is not a completely nonsense distinction to make. This is actually really important. The most important sets that you know of are uncountable. So we still don't have a definition of infinity that works for R. We still don't have a definition of infinity that works for all. We know that these things are not countable. They're not the same kind of infinity as this guy, which we call countable. But they are. We want to be able to talk about the size of any set, and we want to be able to measure the size of any set. We still don't have a definition that works for these guys. So we're not quite done. We want a full definition of cardinality, and so that's kind of what I want to kind of talk about in this video. So, but in order to arrive with a full definition of cardinality, we really need to talk first about ordinality, ordinals. So, to begin with, we need to think more about numbers. So what do I mean by that? Well, I mentioned before in a previous video that everything in math is a set. And I've made some progress towards probably convincing you that everything in math is a set because I defined a function as sets. We defined functions and relations as sets. So now you can see kind of one or two kind of fundamental ideas in math represented as sets. But there's also another thing that we kind of still haven't talked about, like how do you represent as a set, and that's numbers. can we represent numbers as sets? So let's start there in terms of defining our full definition of cardinality. And here's how you do it. Here's how you define a number as a set. So saw earlier, so we can't, I mentioned this before, but you can prove from the axioms of set theory, which I've never done. I've never shown you that proof. It's a simple proof, but you can prove that in any model of set theory, an empty set exists. And this is kind of an odd object because it is an object. It is a thing that exists in the model that represents nothing. It is not itself nothing. It's a thing that represents nothing. There's a big difference there. And you'll see what that big difference is. So define, out of the empty set, I'm actually going to define every number. So I'm going to define 0 to equal the empty set. Fair enough. What am I going to define as 1? I'm actually going to define 1 as the set containing 0, otherwise known as the set containing the empty set. And again, that's why I made this distinction that the empty set is an object. It is not nothing itself. It represents nothing, just like 0 represents nothing, but it is not itself nothing. And so the set containing the empty set is not the same thing as the empty set. That confuses a lot of people until you realize that the confusion regarding what the difference between this thing and this thing is the same confusion that, pre-Enlightenment era humans had about 0 itself. How could 0 be a number? It's sort of the same confusion, but it really is fundamentally a different thing. Now, how am I going to define 2? I'm going to define 2 as the set containing 0 and 1. That is to say, it's the set containing the empty set and the set containing the empty set. So now it's getting really weird looking. This, again, is 2 different objects because these are 2 different objects. I'm going to define 3 as the set containing 0, 1, and 2. And this will be the last one I write down explicitly with empty set stuff. So this is the empty set. It's the set containing the empty set. And then it's 2, which is the set containing the empty set and the set containing the empty set. So it looks terrible. It's starting to look really bad. But you can already see that, I'm not getting everything, first of all. I'm not just taking power sets. There's some structure here that's non-trivial. But and so forth, etc. Dot, dot, dot. So in other words, 21, let's say, that's the set containing 0, 1, 2, dot, 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 up to 20. Every number is just the set of all things smaller than it, where the smallest thing is the empty set. And what's the use of this? Well, in set theory, the only relation I really have, the only symbol relation we have is membership, set membership. In the language of set theory, you've only got one relation symbol. And basically, with formal logic, which we will eventually talk about, you start with a language or a vocabulary. That is, you have a bunch of symbols, Greek letters, and symbols that mean stuff, relations, and so forth. And in language of set theory, it's very simplistic. You only have a single binary relation that is this guy, set membership. And what I've done here in this definition is that I can, here, membership takes the place of less than. So in other words, 2 is less than 3 because 2 is an element of 3. 5 is less than 8 because 5 is an element of 8. And that's exactly how I defined 21, or 8. 8 is the set containing 0, 1, 2, 3, 4, 5, 6, and 7. So all of those things that are in 8, in the set 8, are smaller than 8, and so that's what we've done. Everything is an element. Everything that's an element of anything else is smaller than it. So we've essentially replaced the less than relation with the set membership relationship, the epsilon relation. And so that defines numbers as sets. Now, once you do this, something very kind of mesmerizing happens. Next, consider n, the natural numbers, which I am going to include 0 in this time. 1, 2, 3, dot, dot, dot. This is the set containing all of these numbers. And based on my definition here of numbers, from the above definition, seems like n is as much a number as the other ones. And in fact, it is. This is a number. The natural numbers, as the set of all the numbers, is itself a number. And so that's why you typically write omega instead of n. It's not so much that the cardinality of n is omega, it's that omega is this. This is the first infinite ordinal. This is the first infinite number. And I'm going to stop writing the word number and start writing the word ordinal, because that's what these are. This is the ordinals are the natural extension of finite numbers, and this guy is the first infinite one. So in other words, I have a chain: 1, 2, 3, 4, ... and then it goes on forever. But once I finish going on forever, I've got one number that's bigger than all of those, and that's omega. That's the natural numbers, and likewise can define omega plus 1. How do I define omega plus 1? Well, it's the same way I define the successor to everything else. It's the set containing 1, 2, 3, ... up to omega itself. Right? I didn't have it's kind of like saying it's taking this set and putting the natural numbers inside of it. Just kind of I can just dump this back in, and then I get a bigger thing. So kind of fundamentally, this is equal to omega union the set containing omega. Maybe I should draw that union a little better. And in general, this thing right here kind of works for all the ordinals. So you've got omega plus 1. I've got omega plus 2. Omega plus 2, this is equal to 1, 2, up to omega. And then I add omega plus 1 in there. And this is, again, omega plus 1 union the set containing omega plus 1. And in general, for any ordinal alpha, typically you use letters like alpha, beta, gamma to represent ordinals. For any ordinal alpha, alpha plus 1 is equal to alpha union the set containing alpha. You kind of take the set alpha plus 1 and dump alpha plus 1 itself into that set. And that defines plus 1. And I can do this forever. I can kind of continue this chain here. Here I can go to omega plus 3 and up to, omega plus omega even. That's equal to omega times 2. And, then I can kind of do that again. I can go omega times 2 plus 1, ... I can go to omega squared even. I can just kind of do this omega many times. And I can just go on and on and on. And so this is I've extended numbers to tons of infinities. So this is the ordinals. The set of all these guys, I'm going to put set in quotes, of all ordinals is denoted capital O-N. Now, this is technically not a set. I can think of it as a set because it's a proper class. It's a definable relation to be in the set. But it's not really technically a set within the axioms of set theory. It's too big. You get a lot of logical weird inconsistencies when you declare something like this to be a set. But that's kind of the set of all ordinals. You can think of it as a set, even though it's not. Now, using our definition of ordinals here, we can actually define cardinals. So using ordinals can define cardinals. Or maybe I'll say cardinality. I'll just define cardinality outright of a set in general. And this is going to be a third definition, which is, again, an extension of the second definition. The second definition was not the full story. Here's the full story. So for a set A, define the cardinality of A to equal the smallest ordinal. By the way, these things are called ordinals because they're ordered, right? There's an ordering to all of these things. Everything falls somewhere in this set. The set of all ordinals is sort of itself an ordered set. It's the smallest ordinal such that it's the smallest ordinal, I'll call it alpha, such that there is a bijection from alpha to A. And that's it. So this is kind of, this completely meshes. This is just the natural extension of the second definition we said, right? We said countable means that there's a bijection from omega, the first infinite ordinal, to A. So this is the cardinality of an infinite set. Let's think about this for a second. So this is the full definition of cardinality. It's the smallest ordinal that has a bijection from the ordinal itself as a set to A. Now, consider omega plus 1. What's the cardinality of this? This is a set, right? Everything is a set. What's the cardinality of omega plus 1? It's equal to omega, which is very strange because I said up here, the cardinality of omega plus 1 is equal to omega, even though as ordinals, omega plus 1 is greater than omega. This is where things get really weird. But it's actually very reasonable why omega plus 1 as a cardinal in cardinality is equal to omega. Why? Well, just take the biggest thing and put it first. So in other words, a bijection would look like this. A bijection, again, is just a labeling, 0, 1, 2. So if there's a bijection between omega and omega plus 1, then I can enumerate them. I'm going to have a first guy, a second guy, a third guy. So what am I going to assign to 0? I'm actually going to assign omega. Just take the, so in other words, I'm kind of, here's my whole line that leads up to, whoops, that's a 1. And then omega. This is the whole set. I'm just going to take this guy and sort of paste it over here. And then start there. So I've got this finite number of things, but you just begin with that, and then you have kind of an infinite set, and this is a bijection. So I assign 0 to omega, I assign 1 to 0, and then I kind of go from there. So in other words, f of 0 equals omega, f of 1 equals 0, f of 2 equals 1, and so forth. That's clearly a bijection. So now notice, I've screwed up the ordering completely. I no longer have kind of this is not an order-preserving map. Omega is bigger than everything, but now suddenly it's the smallest. So, I mean, I screwed up the ordering with this bijection. I've done something messy to the ordering itself, but in terms of just the size, in terms of just kind of like identifying how many things are in it, this is a, this is a bijection. And so, similarly, omega plus 2, omega plus 3, even omega times 2. These are all countable. These are all cardinality omega. Why is omega times 2 cardinality omega? Because, again, just kind of note that this is sort of similar to the integers. Right? It's sort of like 2 copies of omega, just like the integers are 2 copies of omega, where you have negatives and positives, and we define that bijection by sort of alternating them. Again, that totally screws up the ordering, but it's a bijection. And so what's really going on here? Let's kind of talk about this. What the heck is going on? What's going on here is something that we've always taken for granted. We've taken for granted until now that numbers, in the way that we use them, have a dual character. I'm going to do some dialectics here. So number one, the first use for numbers is that the numbers, we use them to order things, index things. They represent things in a sequence. Right? I tell you to go to page 58 in a book. I tell you to take a seat at seat 3A, or just say I could say 3A, or we could come up with some kind of numbering, etc. We use them to order things, index things, think of them as a sequence. Think like location in a book, right? Go to page 38, etc. That's the first way that we use numbers. And the second way we use numbers is obviously we use them to measure sizes, amounts, and so forth. So I say that this is like 58 joules, or I'm measuring joules, I'm measuring difficulty, and so forth, right? We use them to measure sizes, amounts, and stuff. And this is why they're called the ordinals. The ordinals are kind of, in terms of ordering, so this is the ordinal use of a number, and then this is kind of the cardinal use of a number. And until now, we've been able to take these two distinct uses of numbers for granted because they coincide. For finite stuff, these uses coincide. But that's not the case in general. But once you get into infinities, these notions diverge in their assessment. These two notions of these two uses for numbers sort of diverge. They cease to be the same. They start to change. And one way to see that, and this is not just kind of like a theoretical like wankery. This is not just math for the sake of math. This has very practical relevance. For example, think about difficulty. We talked about this. In my discussion of difficulty, I mentioned ordinals too. Think about our discussion of difficulty. We mentioned that it's obviously important to have a difficulty scale in which some problems are infinitely more difficult than other problems. We do, that's going to be important. Just think about computability. We're gonna have classes of problems in terms of like their resource consumption and difficulty in that sense. But then we also have problems that are just uncomputable, and we want to be able to say that an uncomputable problem is in some sense infinitely more difficult than the computable problems. So in this sense, our difficulty scale definitely goes past finite numbers. It's an important thing to index. It's an important practical physical thing that we want to index that is going to include infinity. That is going to have, we will have, difficulties, going from, 1 to omega and beyond. And in a sense, when I give you like a problem of difficulty omega plus 1, that will be greater than difficulty omega. But in terms of the set of difficulties themselves, however, the set of difficulties themselves is countably infinite. Well, that's not quite true. But the bottom line is that there's an ordering kind of importance to the difference between omega plus 1 and omega. So like, what I mean by that is like so in other words, let me just write. This distinction is important in terms of order structure. But insignificant in terms of sheer number of things, in terms of comparing the sheer size of each. So if I'm just thinking about like how big is this set, how big is this set, they're the same. There's no difference in terms of size. However, it is important to be able to kind of have this sequence that continues past omega. There's a lot of natural things in reality that it's important to be able to go to omega and then continue counting 1, 2, 3. And in that sense, the distinction is purely ordinal. The distinction is purely ordinal at that point. It's only in terms of the indexing that we care about this. And in that sense, this is different. The order structure of omega plus 1 is different than omega. Right? With omega, I can start at 1, and then I can go to 2, and then dot, 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 and I can keep going forever, but I can never finish. I can never get to the top. Omega plus 1 has like a pointed infinity. It has an omega. In terms of order structure, I have kind of like, it's this versus, this. And likewise, I could have this versus, 2 points at the end, or 3 points at the end, or 4 points at the end. These are different order structures. I could keep going dot, 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 and then have an end, and then have another line that goes on forever. And then, there's tons of different kind of ways in which you want to like order things, and there's a lot of practical uses for all of this. But size-wise, it's a completely different conversation, and that's really what's going on here. So all ordinals are maybe I'll write this down. So conclusion is that all cardinals are ordinals, but not all ordinals are cardinals. That's kind of the conclusion. And what I mean by cardinal is this. So let me define the cardinals kind of formally. So can be defined and denoted. They're denoted with CARD. So this is the set of cardinals, and this is the set of ordinals. So what is a cardinal? So all the finite numbers are cardinals. But that's not really the set that we tend to care about if we're talking about cardinality. Omega is a cardinal. Denote it aleph not. And I think I've used this before. This is the Hebrew letter aleph. And when I first defined cardinality, I said technically it's this, but I'm going to write this. This is kind of why that conversation existed. I'm thinking, when I say that the cardinality of a set is equal to omega, that's true. It's sort of missing the point, though. If I'm thinking about omega as a cardinal, I'm thinking it as an element of this set, not on. But it is still technically correct. It's fine either way to write either one. And a lot of people just hate trying to draw out alephs. I'm having a bit of fun actually writing them out in these videos. But then I can define omega 1 another way to write it is aleph 1 is the least cardinal bigger than omega than aleph 0. It's kind of, I don't even know I really writing this is such an obvious kind of thing to do. It's just I can define the sequence, and this sequence exists. This keeps going. This guy exists because why? This exists by the last thing we showed. It's not necessarily so. This is a thing because we showed that the cardinality of the power set of the natural numbers has to be bigger than omega. It can't be smaller, and it can't be equal to it. So there has to be something bigger. Maybe not the case, might not be the case that, and by obviously this is equal to the set of all problems. It's the cardinality of the real numbers. It's the continuum. So this cardinality, whatever it is, this is the continuum. Might not be the case that omega 1 is the continuum. Right? So what I do know is that I can take the power set of a countable set and get something that's bigger. What I don't know is that I get the smallest thing that's bigger. So in general, it can be shown that the power set of any set A in cardinality is always bigger than the actual cardinality of the original set. And this argument that this general argument is just a generalization of the argument that we made in the last video. It's actually the exact same argument. You can diagonalize out of the power set. If you take the power set, you can always diagonalize out. It's exactly like the proof we did in the last video. But for any set, the cardinality is always bigger. And so because of that, so card, is the set of all of the alepphs. It's actually as big as all of the ordinals. It's an indexed set as big as ON itself. So in terms of like size of sets, and again, you have to be kind of careful or take it with a grain of salt, because the set of all ordinals is not a set. But if we really wanted to think of them as sets, the set of all cardinals, despite not every ordinal being a cardinal, is actually just as big. So that's interesting. But because we've shown that the power set is always bigger, we do know we have an infinite chain of cardinals. We've shown that. But what we don't know is that that infinite chain is given by the power sets. So we have this infinite chain. Let me go write that down. So we have this giant chain of cardinals. And we can construct it, and we can construct a giant chain explicitly by repeatedly taking the power set. So if I repeatedly take the power set, I do generate this chain. So I have two chains. So I have the actual chain of cardinals. I've got 1, 2, 3, ... up to, well, I'm going to ignore the finite guys. The finite cardinals kind of don't matter. They're cardinals, but who cares? We'll start with omega, which is aleph 1, or aleph not, excuse me. We've got aleph 1, aleph 2, it's, aleph 3, etc. This is the actual chain of cardinals. And then we've also got this chain that we can construct explicitly. So I've got kind of omega, which I do know is aleph 0. That's true. But then I've also got like the power set of omega, and we can write the power set of omega. We can write the power set of the natural numbers, but we know that we have also can write the power set of 0, 1, or not 0, 1 to the n. I can also, instead of the power set, I can kind of write 0, 1 to the n, which I now know is actually 2 to the n, because 2 is the set containing 0 and 1, right? Because 2 equals 0, 1. And so I know that when I take the power set, I'm sort of exponentiating. And in fact, that's the case. The power set operator is cardinal exponentiation. So this power set is cardinal exponentiation. In fact, standard notation for exponentiation of cardinals, or for the power set, actually, if you see a textbook, they don't tell you why you're writing it this way. But sometimes, if you have a set A, instead of writing the power set of A, a lot of textbooks will simply write 2 to the A, because they just associate the power set with exponentiation, because it's that closely related. But in any case, instead of writing the reals, I could write the reals. I could also write 2 to the omega. This is like R, just like this is like N. And then I can write, and then I can take the power set again, and that would essentially give me 2 to the 2 to the omega. I can write, and then I can do it again, 2 to the 2 to the 2 to the omega, etc. Now this is a chain of cardinals. And I do know that the first guy is equal to aleph 0. I do know that omega is equal to this. But what about these two? What about aleph 1 and 2 to the omega? I don't know if any of these are true. And the reason for that is because I know 2 to the omega is greater in cardinality than omega. But I don't know if I've skipped anything. So that's kind of the big question. I'm going to write down the big question and summarize it. So that kind of leads us to the big question of like the theory of cardinality. This is the big question. Are there any cardinals? And what I mean by cardinals is like, worthwhile to think about notions of size in between the size of the counting numbers, the countable infinity, and the size of the reals. I know that I have these two cardinalities that are both infinite. I've got the cardinality, I've got the natural numbers, the countable cardinality, and then I've got the real numbers that are they're uncountable, they're bigger, and I get that kind of by taking the power set or exponentiating the original power set, the original infinite set. But what if I've skipped something? And so this is kind of the continuum hypothesis. So the continuum hypothesis is the claim, no, you don't. There aren't. Let me say it like that. There are not. In other words, i.e., 2 to the omega is equal to aleph 1. This is really the statement of the continuum hypothesis. Again, this is a hypothesis, not a theorem. So important. Let's state the general, and then there's one more, the general continuum hypothesis. Is the statement that cardinality, the set of all cardinals, is the chain of power sets. In other words, this sequence, this thing I'm doing here, like this thing I'm doing here, when I kind of repeatedly take 2 to the previous thing, that in fact is literally this. It's all the cardinals. So I get the card. In other words, card. So it's kind of an extension of this. I have this, so omega is obviously equal to aleph 0. That's just true. And then 2 to the omega is equal to aleph 1. 2 to the omega equals aleph 2, and etc. So the general continuum hypothesis just kind of extends this claim to everything and says you get all of it. Now, is the continuum hypothesis true? Truth of the continuum hypothesis. Is this an unknown? Is this just a question that we don't know the answer to yet? Or is this something more? And the answer is it's something more. The truth of the continuum hypothesis is independent of ZF set theory and ZFC set theory. So, I mean, whether or not you include choice, it doesn't make a difference. So what I mean by that is that in mathematics, I'm going to repeat myself a bit, but like this has to sink in. I'm sure people appreciate me repeating myself here. In mathematics, we begin with a set of axioms. And so, like I said, everything in math is a set. In other words, if I prove something to my calculus class, or my pre-calculus class, or any class that I'm teaching, when I'm proving things to my class, it's implicit. It's not told to you directly, but it's implicit that those proofs are proofs within ZFC set theory. Everything in math is ZFC set theory. We have some grand kind of axioms of what is and isn't a set, known as ZFC. And then we basically assume that everybody is kind of working within some true model of ZFC set theory. So, we have a set of axioms for what is and isn't a set. And we assume when we are doing math that we are all, as mathematicians, working in some common model, or like universe, or like model of set theory, some common model which satisfies those axioms. Now remember, I kind of framed this in the very first lecture. I kind of said, like, we have something kind of abstract but real that we want to talk about. Maybe it's the natural numbers. Maybe it's computability. We can't capture it directly, formally, but we can state some things that we think are true about them, and then anything that satisfies those axioms, satisfies that I've discovered truth about it. So, we have some statements that we are assuming are true about the model that we're all sharing and working with, but we don't really understand the model completely directly. And this is a very, I should preface this, I get us in trouble, framing it this way. This is a very Platonist, this is kind of a very Platonic way to think about the incompleteness theorems, is that we have some kind of common model. A lot of mathematicians will take issue with that. I just wanted to be clear that I am very much a Platonist in terms of my thinking about all of this stuff. And some people would take issue with that, but nobody can say I'm wrong, really. But in any case, we have some common model that satisfies these axioms. And so what I mean by the continuum hypothesis is independent of ZF set theory is that there are models of ZF in which CH is true and models in which it's false. Now, of course, in any model, in any fixed model, everything is either true or false. So, whatever the common model that all mathematicians are working with, assuming that you assume there is a common model, assuming that you're taking a Platonist kind of view of mathematics, and you're assuming that all the mathematicians are working with some common model that's real and exists in kind of a Platonic sense, then yeah, CH is either true or false in that model, but we don't know, and more importantly, we cannot know, and we cannot prove it, because there are models of ZF in which the continuum hypothesis is true, and there's models in which it's false. In fact, there's models in which the continuum hypothesis is true, but the general continuum hypothesis is false. You can kind of even go finer than that. And you can build models. You can actually start with a model in which the continuum hypothesis is true, and then basically dump a bunch of real numbers into it and force it to be false and make a new model out of it. There's all sorts of weird things you can do. This is a whole theory of forcing. But the bottom line is that the continuum hypothesis is an example of something that occurs quite a bit in math, that it's a statement that, within the framework of mathematics that we do, within the kind of like the logical universe that we exist in, this is too meta of a question to answer. There are certain things within an axiomatic system that the axiomatic system cannot prove about itself. Maybe I'll say it like that. There are by the incompleteness theorem, this is what the incompleteness theorem says. There are, by the incompleteness theorems, statements which are kind of, in a sense, like which there are statements within within any axiom system which cannot be proven within the system itself, like from the system's perspective. Like, we cannot know. If we're assuming this Platonist view, we are working within a model, and the continuum hypothesis is too meta for an axiom system describing that model to actually prove it or not prove it. Now, we can speculate, but we cannot prove it. There's not going to be a proof for or against this inside of ZFC. It's kind of outside of the logical kind of framework that humans work in, is kind of what's going on here. So the incompleteness theorems there are, by the incompleteness theorem, statements within any axiom system which cannot be proven within the system itself, like, within the system itself. I'm trying to avoid saying the statement too meta, because I don't kind of agree with that, but that is sort of also what's going on. These are two examples. So, I mean, what do you think? Do you think the continuum hypothesis is true or false? Maybe leave a comment and let me know why you think it is. And if you take issue with my presentation of the fact that there is a true model of ZF set theory, let me know what you think of that too. This was just sort of a divergence from computability theory, but I thought it was important to touch on while we were here, because it's really interesting and because it's a really kind of wild pillar of mathematics. So hopefully you found that interesting.